Ladies and gentlemen, welcome to video number 21 in a series of video lectures that are companions to the book The Fivefold Sun, which was filed at the Bibliothèque Nationale de France in Paris in late 2017. We are today December the 3rd in 2018, about a year later. Today we will discuss solar oscillations that have a return period of more than 15 years, i.e. periodicities beyond the Sun's quasi-decadal cycle. Today we introduce the methodology and data in video 21, and in the next videos we will see what the results are. In video 21, we start as usual with the accepted notions in the field. One of the accepted notions is the Gleisberg cycle, which is a detected fluctuation. Another one is the Suess-de Vries cycle, which is another detected fluctuation. You see here the number of results from a search on the World Wide Web performed in 2010, in which you see we have only two that emerge from such an internet search. The Gleisberg cycle, after Rudolf Gleisberg, who from 1935 on found a fluctuation of about 80 years. And then an oscillation with a sharp value of about 207 years, called after Hans Suess or after his colleague de Vries. No other oscillation is accepted and named in the field. Also, these two detected oscillations have an unclear status. As far as the Gleisberg cycle is concerned, in present-day literature in the 21st century, 50 years after Gleisberg, the cycle, so-called cycle named after him, is postulated to last from 70 years up to 120 years. And this variation of 50 years would occur over a time span that is not much longer. For instance, since 1800, it would have varied from 1 to 2 approximately in its return period. This is difficult to regard as a true cyclicality. Let's say that it is considered as an approximately centennial return period. The Suess-de Vries, conversely, as a cyclicality, has a very sharply defined length of 207 years plus or minus 2 years, which is inferred from the spectrum of proxies in the radionuclide records, but no epochs for this fluctuation are known. So we don't know when its extreme epochs are. Is it truly a cycle? Finally, another open issue in the field is that it is postulated that these two fluctuations, and if any, the other fluctuations that might be detected, are not related, except perhaps via a period doubling phenomenon, which in fact we will actually find. The methodological principles retained for the detection of such solar periodicities in the Fivefold Sun project are, as usual, a meta-analysis. It was performed in two parts, one step in 2010 and the other in 2017, about 1 year full-time equivalent approximately in total. And it is similar in method to what was explained in video 20 for the intracycle periodicities of less than 7 years, except that Unlike the intracycle periodicities, we have a span of return periods from 15 years to more than 1,500 years, i.e. From 1 to over 100. So we must include as many data as possible, otherwise our series will be partially empty. So we do not only use the periodicities detected in plotted spectra, but directly from the start we also include the periodicities that are cited by authors explicitly, even though they are not apparent in published plotted spectra. The risk of this approach, but it is inherent to meta-analysis, is that a weight that is excessive might be attributed to the values which are found by teams who repeat similar publications. The datasets that we used in the investigation of 2017 for timescale under review up to 2,915 years in terms of a return period. There are 5 categories in such datasets. The telescopic sunspot number for the interval before telescopes, the naked eye sunspot number, sunspot record, the aurora borealis, the radiocarbon record, which is important because it allows to go much farther in the past, and it is also chronologically very precise thanks to trees and dendrochronology. And finally, the 5th category is a set of diverse other radioisotope records, beryllium, results from combinations of beryllium and radiocarbon records, and oxygen isotope record. We performed mostly in 2010 separate detections for the most important, the most conspicuous return periods. The Hale cycle is well known, but for control we investigated in 2010 in detail the band of the fluctuation for the about 21, 22, 23 year Hale cycle, double the Schwabe cycle, the sun's magnetic cycle. Then the poloidal so-called 3 cycle of about 30 years. An 88-year cycle, which is detected, which was, for instance, proposed by Joan Feynman, her collaborators, many more than 2 decades ago, and for which I wrote a paper in solar physics in 2004, the H-Schwabe cycle pulsation. And finally, we also separately investigated the well-known 2008 year period in 2010. This allows us to ignore in the investigation of 2017 these pervasive return period in the spectra under investigation, so as to leave room for the less conspicuous undetected lengths that might nevertheless exist in the variation bands of the above periods or near the variation bands, especially if we assume that it is verified, that it is true that there is a very large band of variation for such prominent cyclicalities. We have to suppose that there is not much room for other cyclicalities. On the other hand, if there are other cyclicalities that have remained undetected, if we remove those from the data that we investigate in the spectra, maybe we will find what they are. And this goes hand in hand with another postulate, which is that in fact these prominent fluctuations have sharp periodicities instead of large bands. The binning procedure is crucial because binning must be arbitrary, more or less arbitrary. We have same binning for each data set, obviously. And there are 5 bins, sets of bins, a centennial set of bins, half-millennial, millennial, bimillennial, and multimillennial, with arbitrary bounds. The bounds are not at round numbers of years, not at 100 years or at 500 years. First of all, we want to have a bin boundary ending with 5 because there is an overproportion of stated results in the literature with end in 0. And if we have bins ending with 0, we don't know in which bin on one side or the other of the boundary to attribute such values. So we have bins ending with 5, and this will be the most straightforward way to attribute the rounded results found in the literature. The same rationale for the centennial boundary, although it is just an expectation beforehand that we might find an anomalous proportion of results ending with 2 zeros. So in total, we have to add at the centennial or millennial boundaries an excess of 10 plus 5 years, i.e. 15 years, and we start with 115 years. The bottom bound is 35 years because we start arbitrarily from the 30-year poloidal cycle central value, and we add 5 years as defined before. This is now one example of the results from one of these 5 category data sets. This is will be shown now the results from the spectrum of the radiocarbon record after this citation by Hans Suess, one of the fathers of radiocarbon science. You see, he was disappointed that it took about 20 years for science to accept that there was a time spectrum to be detected in the radiocarbon record. So let's see now what this time spectrum tells us about the Sun. In the following table, you will see some figures, some numbers, after which there is the letter G. It means this is given by the cited author. Other values are estimated in this work. So this is the table for the radiocarbon record time spectrum at the centennial scale from 35 years to 115 years. You see in the bottom line here the mean values of the found return periods in each bin, and you see how many reported values contribute to this mean. So we see that in this category we have no predominant finding. The largest number of reported values is only 3. Now for the half-millennial scale, 115 years to 415 years, we have 2 values that have somewhat more higher number of reported results, 5 each. This is the value of 227 years. On the other hand, we have a few troughs that are reported in the same bins. Now, if we look at the centennials, the millennial scale, 415 years to 915 years, we begin to have in the radiocarbon record, which is more appropriate for the assessment of very long return periods, we begin to have significant numbers of reported values. You see, for these 2 bins, either separately or combined, if we allow us to combine 2 bins, we have here 8 values, here 6 values, altogether 14 with a mean of about 500 years. What is interesting to consider the troughs is that there is no trough found in this first bin about 500 years. So here we begin to have rather robust indication. And now if we look at the bimillennial scale from 915 to 2915 years return period, we have a very, very sharp determination at about 960 years with 7 reported values, and another one again, same sharp determination, 2,300 years with 8 reported values. What is interesting now to have the troughs is that we have one at 1,050 years, which is just above the peak here at 960 years. So this is a very useful indication that the peak is indeed below 1,000 years and somewhat a few dozen years maybe below 1,000 years, not a sharp band. Now we show an example of the results combined from all 5 category datasets: sunspot record, aurorae, etc., including all the radionuclides. But in the case of the bin that we will show as an example, from 915 years to 2,915 years, obviously we can rest only on radionuclides because there is no other record. So this is a combination now, this table is a combination of the results from radiocarbon record and from other radionuclides combined with the radiocarbon. We have such a category because it is given in the literature. And then we combine those two and we have a result for the ensemble, the total of the radionuclide records. And we see that not only radiocarbon, but these beryllium and oxygen confirm a value of about 960 for an important return period in solar behavior, and also the value of about 2,300. Also confirmed with 4 troughs now that this peak must be below 1,000 years. This again gives credence to the possibility that these fluctuations are sharply defined and do not cover a large band. The found troughs are foremost important in this line of reasoning. This is an excerpt for troughs found below a 150-year return period. The most prominent trough is at about 80 years, i.e. about 7 Schwabe cycles of 11 years. And it happens to be the best known or the best publicized peak in the literature, because it is the value that Rudolf Gleisberg published and many times documented from 1935 to 1960. It is to be compared with the 88-year peak, and the comparison entails that the 88-year peak, which is very robustly supported by strong evidence, cannot include a variation band of less than 80 years and probably not less than 83 or 84 years, because 80 years is one of the most prominent troughs in the spectra which allow us to reconstruct solar oscillations. The same happens with this second trough at 34 years. This is 3 Schwabe cycle, more or less, to be compared with the 30-year peak of the poloidal 3 cycle, to be divided by 3 to compare with the Schwabe cycle, which means that the 30-year poloidal cycle cannot be as large as 34 years, probably cannot be as large as 32 years, and is also very sharply defined, at least on one side of the band, like this one. This also, by the way, entails, to be discussed in a later video, the fact that if a phenomenon, a periodical phenomenon, does not return 3 times over the same oscillation period, it is supposed in scientific literature not to be a chaotic phenomenon. So the Sun, in this sense, would risk no chaotic behavior. Then, in the methodology of the Fivefold Sun project, we compare the detected peaks with the detected troughs and compute a balance, we call a net count of reports, for a return period in a certain band. It is the number of peaks minus the number of troughs, and it can be used as a criterion for the ranking of the peaks, a sort of a prominence criterion. The final step of this approach of the Fivefold Sun to the detection and interpretation also of solar periodicities in the long term is to find whether some lengths are related among themselves or not related, and if they are, to identify distinct sequences of periodicities. So we will show in the next videos the found results, and indeed there are such sequences of related periodicities that are found in this work, and we will show this in the next lectures. This is the end of video 21. I thank you very much for your attention.